In two-player zero-sum games, the two players have interests which are diametrically opposed. One player's win is the other player's loss. We can use this fact to help the players figure out good strategies. A player can simply try to maximize her guaranteed payoff. By guaranteed, I mean that this is a payoff the player will get no matter what the other player does. For example, player 1 would pick a mixed strategy X that gives her the highest expected payoff under the assumption that player 2 will respond in the way that is worst possible for player 1. This is a worst case assumption, but the worst case assumption is justified in this case. And this is because in a two-player zero-sum game, the goal of player 2 actually is to hurt player 1 as much as possible, and therefore maximizing the benefit to herself. So let's formalize this. Player 1 can guarantee a payoff of V if she can find a mixed strategy X such that X transpose times A is at least as large as the vector consisting of all V's. As a reminder, A here is the payoff matrix of player 1. In other words, the expected payoff of that player 1 gets when player 2 picks the strategy corresponding to the first column of the matrix should be at least V. And her expected payoff when player 2 picks a strategy corresponding to the second column of the matrix should be at least V as well, and so on. Player 1 now wants to maximize this value V that she can guarantee for herself. So she tries to find V and a mixed strategy X such that V is maximized but subject to her having a guarantee of getting an expected payoff of V. The condition that X is in the strategy simplex of the first player just means that X corresponds to a probability distribution. So it's the same as requiring that all entries of X are non-negative. So X is at least as large as the vector consisting of all zeros, and that all entries of X sum up to 1, so that the vector consisting of all ones multiplied with X is equal to 1. Let's assume for a moment that all entries in A in this payoff matrix of player 1 are positive. Then it's in fact enough to require that the sum of all entries of X is at most 1. We don't need to require that it's equal to 1. It's enough to ask for it to be at most 1. Why is that? Well, if the entries of X sum up to something less than 1, then yes, it's not a proper probability distribution, because there's sort of some probability left over where we don't know what the player will be doing. But it's kind of the same thing as saying that there's some leftover probability with which the player does not participate in the game at all. But this would never be beneficial to the player, because if all entries of A are positive, it means the player gets a positive payoff no matter what the outcome of the game is. So when we are trying to maximize V as player 1, it is very clear that we would want to always make sure that the sum of all X values is equal to 1, rather than leaving some probability left over with which we don't play the game. Because whenever we play, we can only win. We can never lose anything. Okay, so with this, we can write our optimization problem like the following. I hope that you agree that this is now completely equivalent to what we had before. If not, maybe pause the video for a moment and make sure that you agree that this is the case. Just verify it for yourself. So this was for player 1. For player 2, we can apply the exact same principle. In a two-player zero-sum game, the interest of player 2 is to minimize the payoff of player 1, because minimizing the payoff of player 1 maximizes the payoff to player 2. So formalizing this again, we get the following optimization problem for player 2. I did not include the intermediate steps here. So again, if you want, maybe take pen and paper and check the result yourself as an exercise. At this point, let me justify this assumption that all entries in the payoff matrix A are positive. So what happens if this is not the case? In that case, we can just make all entries positive by adding a large enough constant c to each entry. C just needs to be larger than the absolute value of the most extreme negative value in the matrix. Think about it this way. We play the original game, but in addition to the payoff determined by the game, player 2 must pay player 1 C units of money extra. This does not change the structure of the equilibria we are getting. It only changes the final payoff. Player 1 now gains more and player 2 loses more. But we can easily adjust for this after solving the game by just reducing the payoff that player 1 achieves by C again and increasing the payoff of player 2 by C. And then we get the correct solution for the original game. Okay, now that we've also taken care of this extra assumption, let's get back to our two optimization problems. What do we notice about them? Right, so you have to look back to the last video talking about linear programs, and then you will see that these two optimization problems are in fact linear programs. And the first one is the primal, and the second one is the corresponding dual. And from the strong duality theorem, we know that the optimal solution, if it exists and if it's finite, for both of those linear programs must be the same. So the optimal value v here is equal to the optimal value w. In other words, player 1 can guarantee some expected payoff, v star, for herself, and player 2 can guarantee that player 1 cannot get more than v star in expectation. And therefore, the two mixed strategies, x and y, that we find when we solve this optimization problem, so these are two mixed strategies for the two players, and they must be best responses to one another. Player 1 couldn't get any more payoff by switching to a different strategy than this x we found, and player 2 couldn't lower the expected payoff of player 1 further by switching to some other strategy than this y she found. So in fact, this gives us a Nash equilibrium. X and y, this mixed strategy pair that we get out of these linear programs, form a Nash equilibrium. These types of strategies, in fact, have a special name. They are called maximin and minimax strategies. A strategy X from the mixed strategy simplex of player 1 is called a maximin strategy if X maximizes the smallest entry of A transposed X. And a strategy Y from the mixed strategy simplex of player 2 is called a minimax strategy if Y minimizes the maximum entry of A times Y. And we call a pair of maximin and minimax strategies a minimax equilibrium. And this is a Nash equilibrium. So, to summarize what we've learned, for two-player zero-sum games, we have learned that a pair of maximin and minimax strategies forms a Nash equilibrium of the game. That also means that Nash equilibria always exists in these games. All Nash equilibria result in the same expected payoff. And we call this expected payoff of player 1 the value of the game. So the amount of money that is paid from player 2 to player 1 in a Nash equilibrium in a two-player zero-sum game is called the value of the game. And the third thing we learned is that Nash equilibria in two-player zero-sum games can be computed in polynomial time. They can be computed efficiently. And why is this the case? Well, because if you think back to the last video, we know that we can solve these linear programs efficiently. So we can solve linear programs quickly, and therefore this now means that we can find Nash equilibria in two-player zero-sum games quickly, because all we need to do for that is solve these linear programs.